Everyone can hear me clearly. So I'm Rishang, and on behalf of my co-authors, I'll be talking about our work on assessing LLMs in generating and interpreting formal specifications. So let me start with some motivation. So Gen AI has been explosive recently, and language models have been shown to be proficient in a lot of NL-based tasks like text summarization and translation. And more recently, with the advent of ChatGPT and other very large language models, we have seen them being used for code generation and other kinds of formal syntax. And in fact, even recently, we've had Devin introduced as they claim that Devin is a full-fledged AI software engineer, meaning Devin can create an application all the way from the inception of the product development lifecycle, so software specification, to creating an application and also debugging any issues. So that's what Devin has been doing. So there's a lot of interest in using LLMs for generating formal specifications. But so if you want to assess the performance of Devin or some other kinds of LLMs in these formal specifications that they're generating, what are the key challenges? So one of the key challenges is what datasets do we use to evaluate their performance. Let's take a look at what Devin used. So Devin used something that is known as the SWE benchmark, and there was a major caveat in their performance where they claimed that they improved performance by 3x over existing LLMs. But they only evaluated on this dataset and on a randomly selected 25% subset. Now what that means is that this dataset, their LLM or whatever they used in their backend has likely already seen some of this data in their dataset. So what we need is we need datasets that are not already in the training sets of LLMs, and this is a problem because as LLMs are evolving, they're going to be using these datasets of the internet for their training again. And so we also need datasets that can be well characterized, not some randomly generated subset or something that's based on some human criteria. Something that is more formal, like the complexity of clauses, is a better dataset to use. And the second problem is how do we automatically assess these LLMs? Now there have been some talks about, in the previous talks about verification and validation. And all of them, even the source code based papers, have a human component where the human is providing the gold standard in some way or the other. So traditionally, humans have been annotating the ground truth, and that has remained the case. So the key question that we are hoping to answer is, can we develop a technique to automatically assess LLMs in formal translation and interpretation tasks, or simply formal translation tasks? So that's our contribution in this paper, where we present an approach for automatic evaluation of formal syntax translation. So the first contribution is automatic ways for generating the ground truth data in a scalable fashion, where we are actually, yes?
My question, will your syntax be in the Boolean, or it will go all to SMP?
It can go to SMP as well, but we have only tested, in the results I'll show it's only on simpler logics at the moment. So automatic ground truth data generation, where we use data generators to scale the data set, and I'll talk more about them when we come to the results. The second one, which I'll be spending some time on, is how we do the automatic evaluation once we have a data set. So we use an encoder-decoder representation for automatic assessment, and the key insight here is that there's no human required anywhere in the process. And finally, we'll present our empirical evaluation, where we show how we've used this pipeline for evaluating some state-of-the-art LLMs. So let me provide some background. So language models, they basically take an input X, which is a series of tokens, and they convert it to an output Y, conditioned on the input. So the sequence of tokens is basically, if the prompt is in natural language, they tokenize it. And the input X also contains a prompt, so which is marked by the red box on the screen. And so here basically the prompt is quite important because because the output is conditioned on the input. If you just give the input, it doesn't know what to do, so you typically give it the task. And so here in this case, I just took the AI Symposium text and asked it to summarize the statement in one sentence. So some other background before I get into the technique is formal syntax translation, which we call NL to SAT, where the input is in natural language and the output is some sort of formal syntax. Now in this example, I've asked Gemini to convert a function or description of a function to source code. So that's one kind, and it could be other forms of formal syntax. And the second part is formal syntax interpretation, where you have something, you already have some formal syntax, and now you want to explain it in natural language. And both of these things have one common characteristic, is that the output should be an accurate representation of the input. And this will be important, as I'll describe in the next slide. So coming to our approach, so our approach is automatic assessment of an LSAT using LLMs. And so given a statement F, typically in formal syntax, so we start off with something already in formal syntax, and this can be generated from a data set. The first step we do is we encode it to an NL description using an LLM. And now if we just pause and freeze at this part of the pipeline and ask how would we do assessment of LLMs over here, we would be like a human would have to provide a natural language description of what the formula is, and then you can use semantic interpretation to see if the LLM produced output is actually the same. But our insight is that if the LLM can actually do formal translation well, it can actually also do interpretation well. So what we need is not a human. Since we have the ground truth formula, we can ask the LLM again that, hey, take this natural language description and convert it back to a formula. And once we have a formula, and assuming all steps of the pipeline are correct, we can actually verify it using an external verifier like a theorem prover. So this makes a human independent of the process. So here's an example. We start off with the ground truth generated from some data set, and we encode it using an encoder, and we ask the LLM to convert it to natural language. Now once the LLM has converted it to natural language, we pass it to a decoder and ask it to decode the natural language text back to a formula, which the LLM does. And now what we can do is we can take the ground truth that we knew and the evaluated formula and pass it to something like Z3, an external verifier, and get a truth or false evaluation. And if the pipeline was correct, the translation and the decoding were loss-free, then you would actually get an equivalent statement. Yes?
Do you delete the chat history between
yes.
the first round?
Yes. Oh, yes. So sorry. That's why the previous example said 2 copies of the LLM, because we don't want LLMs remembering anything. So these are 2 independent copies of the LLM that are working. So there's no context being shared. So key advantages: the datasets can be generated automatically, and humans are not required or minimally required for either providing the verifier or the dataset parameters. And it's robust against hallucinations. Let me show what I mean by that. So many techniques in the literature have explored this problem, and they use LLMs as the self-critique verifier. So what I did was I asked ChatGPT one of the prompts of translation, and I asked it the same prompt again, and I got 2 different answers. Meaning that if we use LLMs for doing these kinds of as verifiers, we can possibly get false positives or negatives. But we don't do that because we use external verifiers, which makes our approach much less susceptible to hallucinations. Yes?
Yeah, one issue with your approach is there's so many ways of saying A and B, and you know, how do you know that the LLM is going to generate all possible ways of expressing a propositional formula in natural language?
It could be, as long as they're syntactically equivalent. So A and not A, and the LLM answers false, they're still they still represent the same formula. Because A and not A is always going to evaluate the false, so the meaning is preserved. And in translation, I could say that this formula is false, or you could say A and not A. So in that sense. But yeah, we can chat about it, yeah. So let me talk about our experiments. So we performed a set of sequence of experiments with propositional logic and first-order logic using several state-of-the-art LLMs, both open source and closed source. And the key insight over here is that at least currently, LLMs are not so performant, at least in formal translation tasks involving some sort of logic. So a propositional logic data set consists of propositional logic, and these are just propositional logic formulae, and use Z3. But let me talk about something that was mentioned earlier about prompt engineering. As you said, rock, paper, scissors, you're trying to get it and you weren't able to get it. So that's why prompts are quite important, and it's nothing to say that in the formal translation task, prompts have to be important as well. So what we wanted to make sure was our prompts are actually capable of bringing out the best performance in LLMs possible. At least we wanted to try that. So we tried different prompts on CNF formulae. Now we tried CNF because CNF are well-structured formulae, and it's easy to, we think it's easier for LLMs to translate CNF formulae. So to get make sure that we have the right prompt for translation, we need to do some kind of prompt engineering. And we also needed to ensure that no hints are passed by the encoding process. So the encoding process sometimes we found would not only give an NL description, would also copy paste the formula. So the decoder would have its work cut out for it. Right, so we had to ensure prompts made sure that the output was such that no hints would be passed along. So this is just what we tried, different prompts on a toy data set of formulae, and we ensured that at least one LLM had more than 95% accuracy throughout the data set to be sure that our prompts are at least allowing the LLMs to do the job correctly, and any errors are coming from within the LLM itself. So this is how the results are going to look like. So there's a lot of information over here. The x-axis is the formula size, which is what we are using for the metric of difficulty or the size of the formula. The top y-axis simply says the binary match on the accuracy, whether the two formulae were equivalent or not. Whereas the bottom y-axis says that when they weren't equivalent, what percentage of the truth table did it match, or how consistent were they? So we can see for at least our prompts, GPT-4 is almost close to 100% accuracy. So let me go to our actual results for propositional logic. So we use the same grammar, but now instead of CNF formulae, we're randomly generating formulae by recursive applications of the grammar. And these are averaged over 5 runs. And what we found out that GPT-4 outperforms other LLMs, but as the formula size increases, the total performance goes to sub-acceptable levels. It's around 50% for these cases. Common failures, so we did some analysis. There's some analysis in the paper as well. They failed to capture parentheses correctly, especially going from formal syntax to natural language. They mess up the parentheses, especially for longer formulae. And there are a lot of hallucinations that are happening. So the second set of experiments is first order logic, and two types of grammars, one with randomized versions of predicates and another with predicates and constants having some English semblance. And we use similar prompt engineering here. And the results are again similar to those of propositional logic, where accuracy is 50%. But surprisingly, even though LLMs are trained on English predicates, what we found is that LLMs are actually slightly worse when converting formal syntax, which is written using some English syntax, and it works better on randomized. So an overall view of first order logic versus propositional logic. First order logic, because it has a more complicated grammar, not surprisingly, it's much more worse than propositional logic and much earlier as well. So in conclusion, we are introducing NL to SAT for assessing LLMs in an automatic fashion with scalable datasets, and we show our approach is robust against hallucinations. For future work, now as we said, there's a different kinds of formal syntax. There's some where humans are providing ML specifications, there's lawyer-based specifications that can be tried. So this framework can actually allow for automatic evaluation of the accuracy. And not only that, but we also want to try to see if there's possible ways to improve the translation capabilities, if we can do some kind of strategies with prompting, like chain of thought. So we tried simple back prompting for now, where we just told the LLM that, hey, this is wrong, can you try to give me a better output? And we only saw a 2% increase, but there's certainly a lot of work that could be done over here. So yeah, thank you for listening to my talk, and I'll be happy to field any questions that you have.